Good evening, everybody. Welcome to tonight's edition of the Triangle Area SQL Server User Group's Advanced DBA meeting. This is our February meeting, first of our 3 meetings this month, and we have the distinct pleasure of inviting Hugo Kornelis, who's going to talk to us about debugging without the debugger. So please, Hugo, take it away.
Thank you, and welcome everyone. Indeed, we are going to do something quite crazy because, well, because I can, because why not? We're going to do debugging without the debugger. Why? Well, I've been to sessions by Bob Ward, I've been to sessions by Paul White where they whipped out the debugger and started typing commands and saying, as you see on the screen, and I was like, I see things on the screen, but I don't understand them, and that's just way above my level. So I decided to keep it simple. It's still a 500 level session, but one that hopefully everyone can understand. And I'm going to do some digging inside SQL Server without using the debugger. So let's get this started and let's see why my clicker doesn't work. There we are. My name is Hugo Kornelis. Welcome everyone. My name is Hugo Kornelis and I make SQLServerFast.com. SQLServerFast.com is a website that you may or may not have heard of that I created several years ago because, let's take one step back. I love execution plans. Everyone who knows me in this community knows that by now. I love execution plans. And I love all the work Microsoft is doing to make them more and more useful. But I hate that Microsoft just fails to provide proper documentation for them. So I decided I'm not going to sit and whine about this lack of documentation. I'm going to write it myself. And that's why I created the execution plan reference. Technically still a work in progress, but almost all operators are there already and other information. Basically, the idea is it's called a reference for a reason. Everything you ever need to know about execution plans should eventually land there. Most of it is already there. So use that resource whenever you need to. Also, there is the execution plan video training that I created after people asked me to provide the same information but in a more accessible way. A reference is not a teaching material. So I started to record video trainings. Um, Over 8 hours of video is already available. There will be even more. Not all of it is for free. Some of it is for free, some of it is not. However, if you buy any of my videos between now and end of March 2024 and you use the code triangle, remember the T has to be capitalized. If you use that code, you will get a 10% discount on all video purchases. There's other content on my site as well, like my blog, like articles, and very important, I have some resources there. If you go to, this is not what I wanted, let's forget that. This, my clicker doesn't do what I want. My apologies. If you go to other than presentations and then presentation resources, you find a list of all the presentations I have ever presented, and you can just click them and download them. So if you want to check the slide deck or the demo code of this session later, then you can. Just go to SQLServerFast.com, other presentations, presentation resources, and off you go. I do a lot of other stuff as well, like working, like doing stuff in the community. The most important thing you need to remember about me is where to reach me. If you have questions today during this session, you can ask them. I believe there's a chat function and Kevin will read these questions to me so I can answer them. However, it is also possible that you have questions later. Then you can mail me or try to contact me on Twitter. I still don't call it my ex. I'm still on there, so it's not my ex yet. So on Twitter or on email, you can reach me. I usually answer pretty quickly. If I don't answer within a week or so, just send me a reminder. I probably overlooked your mail. I get a lot of mail every day, and sometimes I overlook stuff. So we are going to debug something, and what we are going to debug is the window spool operator. Now, the window spool operator, like every other spool, um, is an operator that stores data. That's something that all spools do. They read rows, and whatever they read is stored in an internal work table so that those rows can then be sent to its parent operator more than once. So basically, the spool is used to create copies of rows by storing them in that internal work table. Now, all spool operators do this. The window spool is specifically meant to support windowing functions. The table spool, index spool, and row count spool are three other types of spools that also store rows in a work table and then send them multiple times, but they do it in a different context. We are going to focus on the window spool today. And let's first see what this window spool does in a demo. We will go into what exactly we are going to investigate in the debug without the debugger later. But let's first make sure that we all understand what the window spool does. So for this session, I did some preparation and you see it on the screen. I created a separate instance. This instance was created a few years ago on SQL Server 2017. It's still that same instance, but I'm pretty sure you can do the same steps with every currently supported version of SQL Server. I created a separate instance for testing purposes because I'm going to use some pretty weird settings. One of them is to have tempdb at just a single file. That is not a good practice. But in this case, it helps us because we're going to search for things in tempdb. And if tempdb is 8 files, the recommended number for my laptop, then I have to search in 8 places. By having tempdb at just a single file, I sacrifice some performance, but I don't care about performance. This is just a debug test instance. And I do care about making things easy. I make it large enough to prevent autogrow. I know how much data I'm going to load, but small enough to prevent IAM chains. We'll get back to IAM chains later. So for the demos in this session, 10 megabyte is enough for tempdb. I have also prevented parallelism by setting the system-wide max DOP to 1, and that's all you see in the screen. The rest was all preparation while installing the instance. Now, here is a simple query that uses an aggregate function with an over clause. And the over clause means we specify optionally a window, the partition by clause, and also a window frame based on the order by and rows between. So for every row, we're going to find the maximum carrier number in all rows within the same partition. In this case, the entire table is a single partition, starting 10,000 rows before the current row and ending 3 rows after it, based on this ordering. Now, the output does not necessarily come back in this order because there is no order clause here at the end of the query. But in many cases, and in this case, it does come in this order. That's not guaranteed though. So let's kick off this query and talk about everything that's happening so that we understand how this query works. I'm going to show that in the live execution plan that is already on your screen because this query takes quite a bit of time. So if we follow the data and start at the far right, it all starts with the clustered index scan. And this clustered index scan is an ordered clustered index scan. The index is the PK sales order ID, sales order detail ID. And those who know the relevant tables in the AdventureWorks database by head, like silly me, I know that this is an index that has sales order ID and sales order detail ID as the leading column. By setting orders to true, the optimizer ensures that data is returned in order of sales order ID and sales order detail ID, which is convenient because that is the order needed for determining this window of 10,004 rows. 10,000 preceding, 3 following, and the current row, 10,004 total. Now, after reading those rows, a segment operator marks the start of each new segment. In this case, the segment does not have a segment by or group by column, and that is because we're just marking the entire data as a single segment. That seems superfluous, but a sequence project operator, the next to the left, always requires a segment operator as its direct input. It only can work on segmented data. So in this case, we need to have this segment operator that marks the entire input as a single segment by marking the first row as the start of the segment and all other rows as not the start of a new segment. The sequence project then computes some new values. In fact, it computes exactly one new value by using the row number function. So within the partition, which is the entire dataset, every next row is incremented by one, and we get the row numbers that we didn't ask for in the query, but that are needed as a helper for the rest of the execution plan. So we read some data from the index, we added segment columns, and then we added the row numbers, numbering each row 1, 2, 3, and so on. Then there is a compute scalar, and this compute scalar also computes some extra data, a top row number, which is computed as the row number minus 10,000. Well, that is convenient. That is 10,000 preceding. And we also compute a bottom row number, which is computed as the row number plus 3. Also quite convenient. So this top row number and bottom row number, I already see some of the logic here. SQL Server computes the row number of the first and the last row in the visible window frame of 10,000 preceding and 3 following. So for row number 20,000, the top row number would be 10,000 and the bottom row number would be 20,003. For row number 1, the top row number would be minus 9,999, which is of course a bit insane, but I assume that the rest of the operators know how to work around that and just start at row 1 because there is no row 0 or minus 1, etc. Moving a bit to the left, we now see another segment column, and this segment operator, and this segment operator once again does not have a group by column. So once more, the entire dataset is marked as one single segment. The first row is marked as the start, the rest as not the start. If I had a partition by clause here before the order by, then this segment column operator as well as this segment operator would both have a group by of that partition by column to restart the process for each next partition. It's a modification you can make in the query and then you will see it happen. Now you may wonder why we have two segment operators that both add the same segment marker. And that is a bit superfluous, but just like sequence project, Windows Spool also requires its direct child to be a segment operator. It cannot work on a segment column that is computed elsewhere in the plan. Why? I don't know. It's simply how SQL Server is built. And of course, the work a segment operator does is so minimal that it is almost no performance overhead anyway. Now, the Windows Spool operator is where the interesting stuff happens. And if you look at the row counts, you already see some disturbing numbers there. And you start to understand why this query runs so long. So let's look at what the Windows Spool column does. Let's first look at the data it receives. So if you look at the output list of the segment column, you see the sales order ID, sales order detail ID, and the carrier tracking number that are required for the select list. And then you see these row number, top row number, and bottom row number that were computed, and the segment column that is added by the segment operator. Based on this data, the window spool then returns the same sales order ID and carrier tracking number, the same row number, the same segment number column, and a new column called window count. And you see that the number of rows goes up dramatically. What window spool does is it stores all its incoming data in a work table. Then for each row, it returns the current row followed by all the rows that are visible in its frame. So if we are at row number 20,000, it will return first row number 20,000 and then rows 10,000 until 20,003. And yes, that means that the current row is in there twice, but that is because a frame doesn't always include the current row. And we have to have support for frames where the current row is not included, so we need to repeat it if it is included. So for every row that window spool receives, it sends that row followed by all the rows it sees in its window frame. And it also includes a window count, which is increased by 1 for each row. So for the first row, window count is 1. For the second row, window count is 2, and so on. Now, that sounds like a lot of work, but why do we do that? Because then we are going to aggregate it again. And the aggregate, the stream aggregate we see here, aggregates by this window count. So for every group of rows, it will now aggregate, returning just one row with a sales order ID, sales order detail ID, carrier tracking number, and one new column. Now we do need to find out how those columns are computed. We can do that in the defined values. And let's make this a bit larger. Here you see that expression 1001 is computed as the maximum carrier tracking number. Well, that is the column we asked, well, here to the left of this box. And it computes that over all the rows that are returned by window spool, which are all the rows that are visible in its window frame. For the other columns, like sales order ID, it just uses the any aggregate function, which returns the value from the first row it sees, which was the current row. So here we see how it works. Window spool expands each row to the row plus the entire visible frame, and stream aggregate then aggregates all those rows in the frame to come back with the correct aggregate value. And that is how window spool works and why it is used to support especially this kind of windowed aggregates with a frame. Are there any questions so far?
So far, no questions. Although, if there are any, get them in chat and we'll pass them along.
Yeah, and you can just interrupt me. I might stop a few more times, but you can always interrupt me. Now, the interesting thing is we now know window spool stores a lot of data. In order to be able to return rows 10,000 until 20,003 when row 20,000 is processed, it does have to have at least rows 10,000 until 20,003 in its work table. Perhaps more, but that is the bare minimum. So how is this stored? That is the question I asked myself. And there is some documentation on this available, but it's very limited. The only thing I can find on official documentation is if the number of rows can never exceed 10,000, then it will be stored in memory, and otherwise it will be stored on disk. Now, in this case, between 10,000 preceding and 3 following, we know that the maximum is 10,005 rows, 10,004 rows, which is more than 10,000, so it will be on disk. If I had used between 40 preceding and 20 following, that would have been 61 total, it would have been in memory. If you use a range instead of a rows expression, then it will almost always go to disk because the range includes all the ties and we never know in advance how many ties there will be. So if you have a range instead of a row specification, the work table will always be on disk. If you have a rows specification, then your mileage might vary. I wanted to know how the disk-based work table is stored. But this was all that I could find. How are you going to go there? That was the problem I was running into, and then I realized I have some major problems that I need to overcome. First of all, even the query ran for 6 minutes, but once it's done, because it's a work table in TempDB, when the query is done, SQL Server will release it and the storage will be reused. So I need to be pretty fast if I want to investigate it. Or when I restart the query, I can perhaps find it again, but I have to do some things again. So I cannot just take my time with the existing structures to check them for as long as I want to. And that is a problem because my investigation can take a lot of time. In fact, when I first did this, not as part of a presentation, but because I actually wanted to do this investigation, I started with Table Spool, then Index Spool, then Window Spool. Especially the first step for the Table Spool, the first spool I investigated, I spent a few days, not 24 hours non-stop, but a few hours each day for several days, just trying things, failing, trying again, trying something else, failing again, until I got one step further and then trying more things. But the query duration is limited. So, how are we going to fix this? Of course, some people would say just use the debugger, halt the process. Then everything remains frozen, nothing runs anymore because the process has been halted using the debugger. But I already told you the debugger is way too complex for me. I cannot handle that. And yes, with the debugger, you have unlimited access even to internal memory structures. But for me, it's too complicated. And I also would run into the issue that I cannot even use SQL Server commands when the SQL Server process is halted. So let's say I want to investigate a page that is in TempDB. I first would need to figure out, is it on disk or in the buffer pool? It might be flushed to the disk, or it might be in the buffer pool, or it might be on both, and then it might be dirty. So the version on disk might be different from the buffer pool. And how do I find it in the buffer pool? So many questions that I don't know the answer to. But with SQL Server running, I can just use dbcc page, and SQL Server will figure out whether the version in the buffer pool or on this disk is correct and give me the correct information. And it might even parse it somewhat for me. So I didn't want to use the debugger. I am lazy. I want SQL Server to do the heavy lifting. Now I can of course create a very slow query. If you understand execution plans, if you understand query tuning, you also understand how to untune a query and make it slower. But how slow exactly should it be? Is 2 hours slow enough? Do I need 4 hours? What if I have done a lot of investigation and then I realize I'm nearly there and then the phone rings and my mother wants to catch up with everything that Aunt Dora has told her? And in the meantime, I see the query finish and I know I ran out of time. I need to restart the query, and due to the volatility of TempDB, all the storage locations I just found might be different. I have to do it all over again. So no matter how slow the query is, it's gonna be not guaranteed slow enough. So then I realized, why not use supported functionality? Why should I look into a debugger or into weird things like extreme slow queries when I can just use supported functionality, locks and blocking? And I use this to what I call freeze the query. And I'll show in the demo that this freeze can be held as long as needed. If I wanted to, I could go to sleep and continue the next day. I just had to not switch off my laptop. And I don't do anything that's not supported. I'm only using completely supported SQL Server functionality. So how does this work? Well, let's take a look. We have the execution plan here. The full execution plan is there as well, but we also have the results here. And those results can be interesting, but we will return to them later. But first, let's see what we are going to do. Let's make sure we're in the correct database already. Now, the first step is to run the query. I already did that. Here is the query and the results and the execution plan. We have everything. So I'm not going to do that again. That would be a waste of 6 minutes. Now I have some code here. I'm just going to copy it, create a new window, paste it. What I do here is I go to the same database. I create a table called block window spool. Any name works. The name is not relevant. With the same 4 columns that are in the results of the query. The exact same columns with the same data types and the same nullability. I also looked at the logic of the query to understand and the logic of the underlying data to understand that the data comes from a table with a primary key on sales order ID and sales order detail ID. I don't add or remove rows. So the output is also unique on sales order ID and sales order detail ID. This is a table where I'm going to store the results of the query. However, I'm first going to insert a single row in there using these values. Why these values? Well, let's find them in the results. That's way too far. I wanted to stop the query, to interrupt execution at a point where it is where I have a full window frame, so far past the first 10,000 rows. And I decided I will just pick row number 10,100. That's this row. And you see these values, 46,359, 10,100. And these two are irrelevant. I'll show why in a bit. But the same two values, 46,359 and 10,100, are the values I use here. And like I said, those two values are irrelevant. By inserting this row, I'm going to run this query now. And now that I have inserted this row, and you see that the rollback is commented out, so the transaction is open. This is now an uncommitted insert. But now, when I run the original query again, you will see that it first starts to, I should not highlight part of the text, you will see that it first starts to run as normal. We are now, I'm sorry, I'm doing the wrong version. I should have done this one. My bad. So I have the same query here, but now I add an insert into this block window spool. And I did verify that the execution plan was otherwise completely unchanged. That is an important step because this insert could affect the execution plan. But in this case, it didn't. All the properties of all the operators are the same as well. So I know I don't see the results of this query. There will be no result. I am a fool. Include the execution plan, then execute. We don't get any results because they are inserted into this table. But I know that they are produced in the same results that I would still have visible on my screen if I had it messed up. Always have partial results here. But I know that the row that was row number 10,100 will again be row number 10,100 here because everything in the execution plan is exactly the same. And now you see that the execution plan has halted. Nothing is clicking anymore because the stream aggregate has just produced row number 10,100. The clustered index insert has received it, has already inserted 10,099 rows, but it can't insert this 10,100th row because there is a lock on there, because there is an uncommitted transaction. And now I can go to bed. I can continue tomorrow. That would suck for you also. I'm not going to do that. But this is how I bought the time to investigate everything I wanted, and I could just continue as long as I wanted. And once I was done, I would either roll back or commit this transaction. And if I committed, then I would have gotten an error here. If I roll back, then as you see, it just continues because the inserted row was deleted and we could insert this new row. I'm going to stop this execution. I don't need to finish it again. So the first problem was overcome. I have a method using only supported SQL Server functionality that completely halts the query for as long as I want to. Awesome. Next problem is where to find the objects. And there's a lot of things that don't work. So if I had not removed it, then in the messages here, you would have seen how many IOs there were on the sales order detail table, but you would also have seen a row that says work table, so and so many logical reads. That's why I hate myself for misclicking, because I would have loved to show you, but I'm not going to wait another 6 minutes to do so. You know what? I'm going to kick off the query again. Then in a few minutes we can return to it. But for now, you will have to believe me that it says work table there as the name. Now, if you go to a new query and you type select star from work table, while this query is running or while it is blocked, you will get nothing back because that's not the official name. It doesn't have an official name. So how are you going to fix this? Well, select star from tentb.dbo.worktable doesn't work. What's the name of the object? We don't know. Nothing in the execution plan exposes a name. Can we find it in sys.indexes or even in the deprecated sys.sys indexes? I sometimes look there even though it's deprecated because sys.sys indexes is a bit more technical, a bit closer to the iron internals of SQL Server. Sys.indexes is one abstraction layer higher, but I looked at both and there was nothing that stood out, nothing special. In fact, what I did was I queried sys indexes and sys indexes before starting the Windows spool. Then I started and froze the query. And then with the query active but frozen, I queried sys indexes and sys indexes again. So I could compare the two outputs. Surely there would be one extra row, right? No, there was not. Let me show that. So here is the query, and I'm going to do copy, new window, paste. So now I have two query windows with the exact same query. And I'm going to execute them both. And of course, wait, I'm going to execute them with execution plan because that is needed for the next demo. I have executed them both, and of course, the results in both are the exact same. You never expect differences when you run the same query in two windows. This is preparation. The other part of preparation is to set up my block table again. So I'm going to create this and insert one row in this block table. And then I'm going to run this query again that once more will execute the first 10,100 rows and then stop. And I'm going to wait until it stops. I can, of course, already start doing things now, but I like to wait until everything is stable. There are no moving parts anymore. And I know if I do things now and do the things repeatedly, they will be the same, but hopefully different from before I started this query. So a few more seconds, we should hit row number 10,100 pretty soon. It's a bit slow because I think the software to share my screen and everything. It's the first time I use this one, but I always notice that it's slower when I share my screen when I'm on Zoom calls or whatever. And some programs are really slowing down my laptop. But we should be there pretty soon now. And now everything stops. Only the time counters are still ticking, but the row counters are silent. So here we have the data before I started the query. And as you see, that is 386 rows for 2 queries total. Here we also have the same data, but I'm going to run this query again. So now we have the data while we have a frozen query active. And it's still 360 rows, 386 rows. And you can compare page by page just by using Control Tab, going one page down on both, doing Control Tab again, and you will see that nothing changes on the screen. And I actually did this. Even though the number was the same, I still went through the list, compared page after page, and saw no differences at all. So the work table is not even stored in sys indexes nor in sys.sys indexes. Well, that sucks. The next step was to check whether the object is stored in the underlying system tables. But how do you get at those underlying system tables? SQL Server has done, or rather Microsoft has done a good job of protecting them and making them hard to access. However, there are some tricks I used, like looking at the execution plan to see how many rows were returned by various operators. Um, Comparing the actual data in the system table if there was an operator with a residual predicate. We'll get back to that in the demo to explain what I mean. The problem with comparing the actual data in the system table is you cannot access the system table unless you have a dedicated administrator connection. If you use a dedicated administrator connection, you can have only a single connection active. So you cannot have blocking query in one window, a blocked query in a second window, and a third query window where you look at the underlying system table. So what I did instead was use dbcc page to check the data. That is outside of the scope of the demo, but I'll talk a bit about it. But let's see the steps we went through. So I basically repeated the experiment I just did to look at sys indexes, sys.sys indexes, but now with the execution plan enabled. That's why I already enabled them when I ran the demo just now. So if you look at the execution plan of, for instance, the first query, you will see that a lot of stuff is being done and a lot of tables are being accessed, such as sys object values, sys pal values, sys single object references, sys scop.js, whatever you pronounce it, sys idx stats. You don't need to know this. I didn't know this, but this is where the actual data from the indexes lives. I know that now because I figured that all out. And if I look at this clustered index scan, you will see, whoops, that it returned 166 rows, but it read 220 rows. So there are 220 rows in the table, and only 166 were returned. Why? Because there is a weird predicate that tests some values in a bitmap. Aha! So here is why we don't see the work table. It's stored in sysidx stats, but filtered out. And we have 220 rows here, and in the other execution plan, which was after we started the query, we then should see 220. Oh, never mind. It's the same value. And then I did something I will not show in the demo because it takes too much time. But what I then did was query sys indexes to find the storage locations of sysidx stats, and then run dbcc page on sysidx stats to actually access all 220 rows in that table. None of them were applicable to this frozen query. None of them changed or added or were removed. This just didn't change. So now I know that the work table for the Windows spool is not even stored in sysidx stats. And in a way that makes sense because we only need to store stuff in sysidx stats if other queries need access to it as well, like would be the case with a global temporary table, for instance. But not with an internal work table that is only used inside a single operator. Nobody else cares about it. The operator can just access the data without having to store in sysidx stats where the data is stored, because the operator can keep the storage locations in its own operator memory. So at first I thought I had run into a dead end. But then I realized TempDB is still a database that is used by multiple queries at the same time. If we are going to allocate data in it, then even if that is completely private allocation and we don't share anything about it with the rest of the world, we still need to make sure that that data is not overwritten by another process. And that's when I realized I can look, for instance, at the PFS page, the page free space page, which is page one in the database file. And if your database file is too large, you can get a change of it and multiple PFS pages, which is one reason why I didn't want the temp.db file to be too large. But if it's not too large, then there's just a single PFS page which lists which pages are allocated and which pages are free. The PFS page is always used when someone wants to allocate space in a database. Even in TempDB, if you want to allocate space in TempDB, then SQL Server will go through the PFS page to find a page that is free and not use a page that is already allocated for someone else. And even though the Windows spool doesn't have to share anything about its work table with anyone else, it still has to make sure that those pages are listed as allocated so that a parallel process doesn't reuse the same page. So I'm going to look at the PFS page, look at changes after I start the Windows spool and block it. Find a page that was free before and is allocated now, because that is most likely used for our work table. Then find the allocation unit, and then this was another hurdle that took me a lot of Googling, but eventually I found that there is a DMOS buffer descriptors that you can use to find all pages from an allocation unit in a single allocated page. At first, I didn't find this yet, and I kept following next page, next page, next page pointers, which was incredibly time consuming. Um, and didn't give me the top page. It only gave me a chain of pages at the bottom level of a tree. But once we have those pages, we can use dbcc page to actually inspect their contents. So let's look at this in a demo. Um, let's first close some windows that I don't need anymore. Let's cancel this query. Let's roll back this transaction. This one is finished again. We have our data back. And like I said, you obviously believe me, but now you see it. The work table is actually called work table, but you can, like I said, you cannot query it by that name. It's a symbolic name. It's not its actual name. To find the work table, I'm going to start with basically the same trick we used before to copy a query to a new window and execute it in both. But before I even do that, I am going to cycle the server. I'm going to restart the server. And while I do that, I will tell you why. The reason is when I was busy with this and I ran into a problem. Did I just stop it instead of restart it? I think I did. Yes, my bad. So let's start it again. Um, when I did, I ran into a problem that I didn't see changes. And at one point, I discovered that there is apparently some optimization specifically in TempDB, where if pages that were used are free, SQL Server doesn't directly mark them as free, but keeps them in a sort of spare pool within TempDB so that it can quickly use them for new objects. And that makes sense if you do as much allocating and deallocating as TempDB does. It makes sense to keep your own private stash of pages that you can just use and reuse and only mark pages as free if they are not used for a longer time. And of course, only allocate if you run out of your private stash. So now I have cycled the servers. That means that TempDB is minimal. We have nothing allocated yet except for the system processes. Now I'm going to execute this query. And what we get in the results, I copied one thing too many. My apologies. What we get in the results is the data from the PFS page. And you see that it lists which pages are allocated. 156 to 159 are allocated. Page 160 is not allocated. And so on. It lists that for all the pages. So we have the query here, and here we have the exact same query, and of course in both windows we have the same results. But now we're going to set up the block again, start the query, and wait a bit until the query has processed the first 10,100 rows and is blocking. Few more seconds, and then we should be there. Then everything is stable. We have no moving parts anymore, and I can freely investigate the table. So I'm going to keep this window as how it was at the start. So here we have the data before the window spool even started. Here we're going to execute the query again, and now we have the data after the window spool started. So on the first page of the results, Control tab, not Alt tab. On the first page of the results, there is no difference at all. So I'm going to page down on both, and again, we see no difference at all. The clicking here is me constantly doing Control tab. And now page down. And again, other than some status bits that we see here, there is no difference. But I keep going down until I find a difference. And this is always a surprise for me where I will find the first difference. It is not always the same. So bear with me while I search for a difference, making sure not to overlook anything. Ah, there I see a difference. Look at this row and this row. You see, before we started anything, page 144 was allocated, but page 145 was not allocated. And now page 144 and page 145 are both allocated. So page 145 is a new allocation. That means it's likely, not yet 100% sure, but likely that this page is allocated to this internal work table. So let's look at this page. And I'm using page dump style 1 here, which means don't interpret the data, give me the raw data. Now that is a terrible style to use, but the reason I do that is when you use style 3, you get an error. Or rather, in this case, not because it's apparently a different type of page, but I'll show you that later. There is a reason I use dump style 1 in this case. what we see here is some data, and we see an allocation unit, and we see a negative object ID. And that is also a confirmation that this is an internal object, so it is very likely to be the page we wanted. And now I'm going to use the allocation unit, so I'm doing Control C, and I will paste that in here, not with Control C, that is not pasting. Control V to paste it, happens to be the same number this time. And now I can execute this and I get an overview of all the pages. And indeed, that's the reason why dump style 3 worked. This happens to be the IAM page. Usually the first page I find is a data page or index page, where dump style 3 does not work for work tables. That's why I told you that, and I will show you that later. But now we know that there is an IAM page, an index page, and a whole bunch of data pages all allocated to this work table. And I can look at all of them. So let's start with the index page, page 289. Copy, scroll down here, paste it in, and here we can see indeed if I use dump style 3, I get an error. The reason is dump style 3 does some interpretation based on data in system tables, but those system tables, we already found that, are not filled for work tables. So DBCC page cannot find the data it needs to interpret the data. So the only thing DBCC page can do is the raw dump style 1, which gives us the information we need in a hard to access format. We will return to this later. However, for now, I know this is the an index page and not the data page. So I know that I need to look at the last 6 byte pairs to find a row number and a page number. And a byte pair is always read in SQL Server right to left. So we have 0001. Those 2 bytes are the file number. Obviously 1, because TempDB is just a single file. And then we have 00000120. And that is a hexadecimal number. So let's bring up the calculator. Let's go to the programmer view. 0120 numlock, and that is decimal 288. Well, that should not be a surprise, because when we looked here, we also saw that page 288 is indeed a data page, and now I know it's the first data page. Returning to the output here, you will then also see that the next page here is 0123 218, which is, I forgot the number again, 200. I've got it here. I don't have it here anymore. Let's just run this query again. The first data page was 288, the next was 290, and so on. If I want to look at the data page, here dump style 3 is even more dangerous, because again, DBCC cannot interpret it, but instead of throwing an error, it simply does nothing. It says, oh, there's nothing on this page. That is a lie. If I use dump style 1, you will see that there are in fact rows on this page. This is row number 1. This is row number 2, row number 3, and so on. And I was so excited when I saw this, because I saw 4911-403C-98 and similar values. And those are values I expected to find, because they are the data that I expect to find in the spool table. So I now have it confirmed, I did find the work table where this data is stored. Awesome. I now just need to decipher it. And for that, I will return to the slide deck. Kevin, is it okay if I go over a bit, or do I need to make sure to finish by 1?
Nope, you're good.
I can spend more time?
Sure.
Okay, cool, because otherwise I would need to rush this, and I hate to rush this. So I found the data, but I still need to figure out the structure. Um, to understand what we expect, how the structure works, it helps to understand what we expect. So I returned to the execution plan and I looked at what data is sent by the segment operator to the Windows spool. And I already showed that in the demo. These columns are returned by the segment operator to Windows spool. So anything in the work table has to be these columns. There cannot be anything extra. I don't know if everything is stored, but it has to come from here. I also looked at what Windows Spool returned to stream aggregate, and you see that there is a large overlap. So the column sales order ID, sales order detail ID, carrier tracking number, and row number 1005 are both in the input and in the output. It makes sense to assume that they most likely will be in the work table. The same goes for segment 1009, although I could imagine that it also just uses some internal logic to read the segment column, do something, and then produce the same data again without storing it in the work table. But it might be there, it might not be there. That was more for me a probably, but not certainly. I fully expected the top row number and the bottom row number to be there because, well, you kind of need them. Why do you need them? Because if you think back of the example, we used rows between 10,000 preceding and 3 following. So when SQL Server reads the very first row, it already needs to give stream aggregate a complete frame with rows 1 through 4. So it has to read ahead, and now it has read rows 1 through 4 so that it can produce the first window frame. But then we need to go to row number 2, which we can't get from the input anymore. So we need to get row number 2 from the work table. But we also need to know for row number 2 which rows we need to return to stream aggregate, minus 9,998 until row 5. I know that, but the Windows spool needs to know it, so this has to be stored in the work table. The window count 1010 is not coming from the input, is only computed when Windows spool does its work, so I don't expect that column in the work table. So basically what I expect is everything that segment returns to the Windows spool with a small question mark for segment 1009. And not window count 1010. I expect that to be produced but not stored in the Windows in the work table. Then I turned to my trusted copy, and normally I would now hold up the book, but I mislaid it. I don't know where you see me already looking. Normally it is here to my left. It's not there now. I don't know where I left it. I use that book so often. And yes, it's about SQL Server 2005, but so many things in the internals have not changed. And Kalen Delaney did a great job of describing them. So whenever I need to decipher DBCC page output, I always leave to the correct pages in that book to refresh my memory of how exactly the rows are stored on disk. You don't have to put things in your memory if you know where to find them. I know where to find them. It's that book. So let's first look at the index rows in the root page of the index. And here is a screenshot that is not exactly the same as we saw before because I created it when I did the same demo at another time, but rows were at different locations then. And in an index page, we have pointers to pages. So if pages are allocated differently, we get different pointers. The logic is the same. So we could do the same with the screenshot I took today, and then some values would change, but the logic would be the same. So looking at the first row, the first byte says this is an index row. It has no null bitmap. The value 06 basically is not a normal value. It's a bitmap. So you should read it as in binary 0110. And that means that bits 2 and 3 are set. and those mean it is an index row and there is no null bitmap. Then at the end, you see the marked location on the screenshot is the page of the next, is the file number of the next page and the page number. In this case, it's 0118. Again, reverse Polish notation 00000118. In hexadecimal is page number 280. This value makes little sense, and it had me stumped for a bit until I realized it's the first index entry of the first page. SQL Server never uses this value. SQL Server only uses this value on the second, third, etc. index entry, never on the first, because it's used to determine whether a certain value goes before or after this entry. And this is the first entry, so nothing goes before it. The value is unused, which means that when SQL Server creates this data, it just doesn't put anything there. It doesn't initialize it. It just leaves there whatever happens to be there in memory or on disk when this page is created. So it's just garbage what you see here, and we don't need to look at it. But for every next row, it becomes irrelevant. So for row number 2, the status byte changes to an index row with a null bitmap. And we see at the end that there is additional data there. So we have the same page pointer to the next page, in this case page 282. And we have an actual value there, hexadecimal 71 or decimal 113. And this is 8 bits. This is most likely a row number. Remember the row number column, row number 1005, I think, that was computed in the execution plan as a helper. That is stored here as the index key. And then to the right, we also have a number of columns. One, well, we already knew that, the value is 113, and a null bitmap that says there's nothing null in this case. And we can look at the same for every next index row, and we will see that the third index entry says that page 283 starts with index key 225. And this is just a regular index page for, in this case, the root page of an index. Let's now also look at the data rows. And here we have a screenshot of the data. And in this case, it does look exactly the same because this is all data. There should be no differences between this screenshot and what we just saw in the demo. So let's decipher this. Again, we start with the status bytes. And for a data row, that's 2 bytes. And value 3000 means it is a data row. There is a null bitmap, and there is at least one variable length column. All the data is encoded in those 2 bytes. After the status bytes, we always get the end of the fixed data. So we know that at position hexadecimal 5, so that's decimal 37, that is where the number of columns is stored. So let's look at that location. That's a bit of counting, but that's these 2 bytes. And here we see that the number of columns in this row is 8. We have 8 columns total. That is both the varying length and the variable length. After that comes the null bitmap. We know there is a null bitmap, and because there are 8 columns, the null bitmap is a single byte. For 9 to 16 columns, it would have been 2 bytes, and so on. This null bitmap says nothing is null, all the values are actually there. After that, 2 more bytes gives us the number of variable length columns. So we already knew that there are 8 columns total, and now we know that 2 of them are variable length, which means we also have 6 fixed length columns. Because we have 2 variable length columns, we now have 2 internal pointers to the end of each varying length column, or rather, no, to the end of each varying length column. So the first variable length column ends just before position hexadecimal 2e, which, and then end of the second variable length column is just before position 4, 6, which obviously is the end of the row. This is actually a bit superfluous that it's stored, but that is how SQL Server stores its data. So if you look at where the first variable length column ends, you see it ends exactly where it begins. It is 0 length. Now that is sometimes valid in SQL Server, but of course if I look at the value of a 0 length column, it is very hard to figure out what it means because it is empty. So I'm going to skip this one for now. I'm going to return to this later and try to understand what this column is. But now I want to go to the second, which ends at the end of the row. And if you look at the data, and here the ASCII translation onto the right side helps, you see that this is the carrier tracking number that we did expect to find in the work table. And if you looked at the data types, you will recall that it was defined as an nvarchar, not as nchar. So it is indeed variable length data, even though it's actually the same length on all rows in the entire table. The declaration is nvarchar, so it is stored as varying length. So we found the carrier tracking number and one mystery column that is varying length. Let's look at the fixed length column. And in the data row, there is no information about how long they are, how many bytes each is, what they are. That is normally stored in the system tables, but not for us. The system tables are not used here. All the data is kept internal in the operator, so I need to reverse engineer it by just looking at the data. Now, luckily, the start makes sense. If you read this right to left, you have a lot of zeros and then 1. Just 0.00001 hexadecimal, that's also one decimal. It makes sense that this is the row number. By the way, interesting finding, we are we froze the query while we were on row 10,100. At that point, we still needed rows 100 through 10,103, but apparently row number 1 is still in the work table. The work table is not cleared out in between. Everything is kept there, even when it's no longer needed. That makes sense because deleting it is quite costly. Now, a bunch of zeros and 1 is the row number. That makes sense. The rest was a bit harder, but I actually did the reverse process. I know that I expect to find a sales order ID. I can look in the data returned from the original query to say that in row number 1, the sales order ID is 43,659 and the data type is integer. I know how integers are stored in SQL Server, so I know that 43,659 is stored as hexadecimal AA8B. And hey, we have 0000 AA8B reading right to left. That, so here I took the reverse path to find the integer with this value that I expected. So the second fixed length column is the sales order ID. And then we have an integer, 4 bytes instead of 8, with the value 1, which is the sales order detail ID I expected to find on the first row. We are getting somewhere. We already have 3 columns. And then the next value is 05, F1, D8, FF, and I scratched my head and I looked at it and I wasted a lot of time. And then finally, after dinner, I decided, happened to have dinner ready at that time, I decided, you know what, I'm going to leave this around because I know where the fixed length ends. So I started working from left to right. I'm in a conundrum now. Let's now work right to left. Let's look at the last fixed length column. Hey, a bunch of zeros and then 04. That's the bottom row number that I expected to find, 1 plus 3. And now that we know that the fifth column starts with FF, 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 that is how negative integers are stored. And indeed, FFFFFD8F1 happens to be exactly minus 9,999. 1 minus 10,000. Another value we expected. And now I understood why 05 F1 D8 didn't make sense, because the F1 D8 was part of a different column, and 05 is in its own the fourth fixed length column. But what does 05 mean? And why is it FE on the second row? And this one had me stumped as well for a long time, until I noticed something when I occasionally switched off SQL Server, did something else, and then the next day returned to it. And so at one point, I noticed something strange with this data. It changed, and it should not change. Index pages are allowed to change when the data is allocated in different places. Data pages always store the same data. How can this value change? And then I noticed something else. It's always odd on the first row and always an even number on all other rows. Okay, granted, I didn't check all 120,000, but I checked a lot, and it was an even number on all rows except the first row. And that's when I realized this single byte is actually a single bit. The other 7 bits are unused. So SQL Server just leaves those at whatever value they are. And that's why between subsequent rows, I don't always get the same value. But the 8th bit that determines odd or even, or rather the first bit, 8th bit, depending on how you count it, but that one bit, that is always the same, because it's always an odd number on the first row and always an even number on the last row. So the fourth fixed length column is not a byte, it's a bit that is set on the first row and not set on all other rows. That's the segment column. The segment column I expected with a small question mark. Question mark becomes an exclamation mark now. I now know that this 8th bit is segment 1009. And now I have identified 7 of the 8 columns, which are the 7 columns I expected. But why is there still that 8th variable length column that is 0 length on all the rows I looked at? Not just the ones in the screenshot, not just the ones in the demo. I looked at hundreds of rows within the 100,000 row data. It was always 0 length. And I will admit, I probably would not have figured this out if I had started with the table spool. But I had already figured out, with the window spool, I should say, but I had already figured out the table spool and the index spool. I had already discovered that both the table spool and the index spool always use a clustered index and always declare them as non-unique, even when they might actually be unique. And here I had a clustered index. Based on the index pages, I know that this index is on the row number column, which of course by definition has to be unique. But SQL Server still declares it as non-unique. And because the clustered index is declared as non-unique, SQL Server adds a unifier column. This column is not used for unique values, but because the index is declared as non-unique, it can be set to 1, 2, 3, etc. if there are non-unique values to create unicity. But it never happens for this work table because the row numbers are already unique. So that's my theory, that we have a unifier here, which is in our case always empty and never the 4-byte ascending integer that could otherwise have been used in regular non-unique clustered indexes. And that is how I figured out how Windows Spool stores its data without ever using the debugger, using only supported commands in SQL Server, using SQL Server against itself to give me the information that SQL Server tries so desperately to hide from me. Is it useful? That's for you to figure out. I had a lot of fun doing this, and I have a lot of fun presenting it. We found the structures, we found the objects, we figured out the structures, and we read and interpreted the data. And now I know that a Windows spool, if it uses an on-disk work table, uses a clustered index on the row number column, which is unique, but it still declares it as non-unique. It stores all the input columns in that work table, and that's it. That's all there is to it. Sometimes the journey is way more interesting than the destination. The destination I could have done in 1 minute. The journey I struggled to present in 1 hour. Are there any questions at this time?
So no questions in chat. There was actually a comment from Anders saying that it's hard to come up with questions when you answer them before he can even type them out. So well done.
My pleasure.
But yeah, in chat, people are saying outstanding job, awesome presentation, enjoyed it. I completely
Nice to
agree.
hear. Good. Well, I have my email and my Twitter on the screen again in case you need time to digest the information I gave. I understand this is, even though I didn't use the debugger, still some pretty advanced stuff. So if you did digest this and the questions come up later, feel free to let me know. I'm always happy to help. I really enjoyed giving this presentation. I hope you enjoyed it as much as I did. And I believe that somewhere during fall, I don't know the exact date, I will return to this group with another exciting internal session.
Yep, we've got you booked
So,
sometime later in the year. Tracy knows.
yes. So tune back in later. And in the meantime, I'm sure that all other speakers that Tracy and you select are awesome as well. I was happy to spend time with you, and I'm happy that you stayed here, even though I went way over. How much exactly? Oh my God, 15 minutes. I'm terrible. Um. Anyway, thanks, and thanks for having me.
Yeah, of course. Thank you so much for an excellent presentation. So everybody remember, next meeting, main meeting will be in person only next Tuesday. So check that out, meetup.com/trypass. And until we see
Bit
each
far
other.
from me.
Sorry. Yeah, it is a little far. But that's okay.
Yeah,
That's all right. We'll excuse you this
but
time.
enjoy the meeting.
Thank you kindly. And until we see each other, everyone, in a future TryPass meeting, take care.